topic. We'll be talking about the ultrafast optical physics behind the generation of higher harmonic generation and the supercontinuum. Now, it turns out that HHG, that's high harmonic generation, is essentially a nonlinear optical process. That we have to realize that. You put in one color and you get the higher harmonics. So we're going to focus on the nonlinear optics of the effects describing the supercontinuum and then the higher harmonics. It turns out the supercontinuum generates the cell phase modulation, full wave mixing, stimulated Raman, and also higher harmonic generation. And higher harmonic generation is essentially the key behind generating the ultra fast pulses in the attosecond range. And that led to the Nobel Prize last year, essentially is the generation. And we have some of the pioneers in the audience and on the web we're going to be talking about their work in this area. And we have a distinguished colleague of mine who used to work in New York and now went to Ohio. And so my name is Robert Alfano. This is the book. And then we'll be talking about what happens in the peaceful world of nature. It seems peaceful, but there's really a riot of activity. And you need a clock. You need a clock to see what's going on in that world. And the second hand of your clock will be the laser pulse. So the laser pulse indicates your resolution of what you can see in the molecular world. And we went from picoseconds to femtoseconds and now attoseconds. And it turns out that attoseconds probes the electrons, while the picosecond and femtosecond probe the molecular motions. And essentially behind these processes that occur in the molecular world is the salient properties of light. We all use the salient properties of light, which we all know is the wavelength, which is the color, is the supercontinuum again, and then the pulse width. This is where you have picosecond, femtosecond, attosecond pulses. And you have the polarization. The advantage of light over electrons is that we have polarization, we have coherence, we have wavefronts. Wavefronts are the new physics, optical physics that we do today. We have not, all we're taught plane wavefronts. We're plane wavefront, and that essentially. However, now we have hurricanes. In Florida is very important. We have hurricanes, which are essentially twisted light, and they spiral. And this adds orbital angular momentum, which is essentially with the moon going around the Earth, is essentially orbited and it spins. So light also can have orbital angular momentum, which are called optical vortices, or helical vortices. Come in with a plane wave, now comes these twisted light. And we use these properties on the light emitted. We all know about fluorescence spectroscopy and absorption spectroscopy and Raman scattering and elastic scattering. So we use these salient properties depending on its color. And that color not only goes to the visible, it goes into the near infrared, and now enters the UV, or extra UV. And then beyond the extra UV, we go into X-rays. So that's where the whole thing goes. And this slide gives an overall picture of my talk. This is essentially so supercontinuum now is going to used to consist of only cell phase modulation, full wave mixing, stimulated Raman, cross phase modulation. Now we're tapping on HHG. So HHG is essentially still part of what I call the supercontinuum. And it all comes from, where does it come from? The laser pulse. So the laser pulse goes into the material, you have a femtosecond pulse or picosecond pulse, and you generate from N2 and N1 all these nonlinear processes. I'm going to bring that forward. And I restarted this work in 2020 after 50 years. 50 years ago, when I was a baby, maybe 1 year old, and I discovered, you'll see in a minute, we meet this colleague of mine, Shapiro, on General Telephone, don't know if people ever heard of GT&E, but that was the main lab in competition with Bell Telephone. We were 200 scientists in Bayside competing with 20,000 in New Jersey. It was like the little Marines. Anyway, we've always copied, General Telephone was always copying Bell Telephone, until Shaquille and I got together. And then we came, also discovered this white light. But that's a second story. Let's go back. Why I say the supercontinuum. It's the laser pulse that comes in to drive, drive, which you're going to show us, these slides I'm going to show you, drive the nonlinearity. You have to assume, everybody has to assume of this theory is that you have a wave. And then in this wave, you have this index of diffraction, which is N2 and N1. This has got to do with chi3, this has got to do with chi2. But these are the nonlinear coefficients of the index of diffraction. Now, I had a lot of arguments with the journal of the OSA, where the guy is, optics, there are a lot of fights with them, and also optics communication. And I'm not using, when I was trying to explain this HHG, using classical ENM, they said to me, it's not a quantum. Not a quantum. I said, does NASA go to the moon with quantum mechanics? I doubt that. I see nothing wrong with ENM theory. And I think Blumbergen would turn it in his grave saying you can't use that. Anyway, that didn't matter. I freshly got it published. And now I think people are talking about it. Hopefully some of my friends here, Lewis, with his thoughts on it at this point. And Chet is on the web, hopefully hearing his talk. These guys are pioneers in the HHG. But essentially, this is the slide. This slide says the energy of the laser pulse is coherently converted to a supercontinuum. And what do I mean by the supercontinuum? This slide shows a picture. After this, we don't have to do anything else. We have the laser pulse coming in, and it broadens. This is the normal self-phase modulation or electronic self-phase modulation, and this is the laser pulse. About 100 times conversion, depending on the pulse rate. You can totally convert to supercontinuum, or maybe 100 times. But what's new is this 3, 5, 7, 9, which is not much less intense than the main pulse. It turned out, Shapiro and I, in one of the papers, talked about 3, 5, 7, 9. But we said, working argon liquid, which we made in 1970, we made liquid argon, which couldn't buy. Couldn't buy liquid argon. So we bought liquid argon. We made it. And we generated supercontinuum liquid argon. And the theory that I put forth in 1972, which we probably may see, is that I said, well, we don't see 3, 5, 7. We have to not see this, we drop that. So we dropped 3, 5, 7, and we kept on going on explaining this one. That was a mistake. That was a mistake. We were in the forest. We made a big mistake. And at General Telephone, we had a lot of pressure to do something new, not dwell on something that we just created. So we got out of that in 1972. Not looking for 3, 5, 7. We just didn't even think it's real until the new work came in the 1990s, and they saw 3, 5, 7, 9. And that became higher harmonic generation. And higher harmonic generation is essentially the forerunner of outer cycles. And now I'm pushing, if my theory is correct, and my theory is the current theory. The current theory is correct. You should go to septic swings. You'll see that you can go to septic swings. Based on the simple theory of N2. So this is the key slide that you use, the spectrum you see. Also, you might notice there's a negative frequency. I'm going to put this forward so we're ahead of time. So negative frequencies. Big question. Now, let's say this laser goes to 2 omega. You put enough power, and it goes to 2 omega. 2 omega. This stands 2 omega. This means this goes down to 0. So the supercontinuum, based on self-phase modulation, can go from 2 omega to 0, covering the entire electromagnetic spectrum. And then if you go a little higher in power, this edge works into the negative frequency. What that means is a different story. I'm not topic of my talk today, but I like to bring it forward that there's a possibility of this thing going negative. What that means, usually in the optics course I teach, I say that's physically impossible. So now, the focus of this talk, hopefully people in the audience will see that it's going to be an alternative model. I use the word alternative. A more universal model to describe HHG and to possibly get the other second pulses. It's based on this N2, which you will see in a minute. Here it is down here, based on the Kerr effect. This is the Kerr distance. The whole thing is based on writing N, the index of refraction, times the normal index, plus is N2B squared. There's also a possibility of doing, if you're doing it in a uniaxial crystal, you get kind 2, and that generates even harmonics. So that's been seen. That's been seen by Rice Stanford. He says that the contact he saw even harmonics in the crystal. So, and they couldn't explain it by this theory of quantum mechanical time resolved Schrödinger's equation. That's the theory they used to explain HHG. That's again the theory of Schrödinger's equation, time resolved Schrödinger's equation. And there's a big controversy, because the E&M theory, the Kerr effect theory, generates a wavelength dependence on the pump different from the wavelength dependence of the time resolved quantum mechanical theory. But I think I can reconcile that at this point. So hopefully my friends here will tell me if this is correct or not, or the idea is correct. We'll talk about that. So, whoops. So, no, I haven't figured it out. Okay, so this model here, quantum mechanical, time, it's really quantum classical, time-dependent Schrödinger's equation. It generates an electric dipole moment, quantum mechanically, E squared. That's what they plot. Hopefully, check this out. They plot this. Kuhn was one of the first papers that I read on this that talks about D squared, and you got the same harmonic generation. Now, we're going to be basing our life, this theory. I haven't done experiments, I'm starting to do experiments now. It's based on light being a wave. That's one problem. Light being a wave, there's no problem about that. And that the index of refraction is essentially as above by derivative. Well, Kerr said N0 plus N2 is the Kerr index. And then there's a difference, it's just that we have to reconcile that the pump wavelength difference between the dipole radiation and the EM are different than 1 over lambda squared. They say the theory, I'm not right or wrong, they say it goes as I times lambda squared. And we will show that it's all consistent with 1 over lambda squared. Now, let me just briefly describe for you so some of the people here don't understand this supercontinuum. Laser light is a red laser. Green pointer there, that's a laser coming here. There's one color. So delta lambda, spectral width, is much less. But the supercontinuum is with all the colors. It's white. So we did it, it was white. You can see the picture. White, and the spectral color, the whole is. In those days, we didn't have CCD camera. We had just film. Polaroid film or so right now it started from UV over to red. Now it expands to infrared, and according to my first slide, it goes into the UV and X-rays. It's always been that most people are using fibers, and their fibers just generated up to about 400 nanometers. If you go into a gas cell, absorption, you get this fiber. So But these are all nonlinear effects based on chi2. And that's the second order of chi2. And then you generate nonlinear. And to stimulate it wrong, you have four-way mixing. That's the non-collinear, using the egocentric effects. Any questions? Okay. Now, as the assumption of my assumption. Electric field laser. Electric field laser has got an envelope. And inside the envelope is the color. That's the frequency. Okay. You have a cosine wave. It's a cosine. It's p at 0. This is 5 femtosecond. Doesn't matter. It's absolutely 0. The fact is that the envelope is going to drive the phase v into coherent. Think of the wave E0 cosine pulse rate. Pulse rate is going to drive the phase. And it's the cosine of the cosine. Remember this, it's going to be the cosine of the cosine squared. And if you had a good special function course in theoretical physics, somebody in your degree, if you had a great professor, would tell you that the cosine of the cosine squared is a bunch of Bessel functions. Not very few people know that. I happen to know that in 72. I was doing my PhD. I knew that after. It's not all about it until recently. So we're going to say that the envelope drives the phase via N2 coherently to produce the supercontinuum. Now I have included in the supercontinuum HAC. So you're going to see that. The peak-to-peak cycle is around 1.6 femtoseconds. Remember that number, about 5 femtoseconds, maybe 2 femtoseconds, then the wave. Therefore, okay. So here's the fundamental understanding of what I'm trying to say. Back in 1875, I don't know how these guys did it those days. He had a battery. Put a battery on a cell, and he put a DC field on a cell, liquid cell. And he saw the image refraction change, and it changed the light going in. It changed from linear polarized to elliptically polarized. That's a big deal. And then, almost 75 years later, this guy Buckingham, he was correct. I have a power supply in 1950, 60 power supply. Turn it on and off, turn it on and off. He did that. He got the AC curve effect. And in his paper in 1956, he gave three important statements. That there's no reason why the index of refraction cannot be instantaneous. Because he did AC, an AC field modulator, the basis of electromodulators. So you put a pulse on the crystal and you modulate the light. So he says that instantaneous. And then if you average over many cycles, is that what normally you see. Most people see when you average over a few cycles, and then what happens to this guy, you average this average, you get e squared over 2, because that's the cosine squared. Cosine squared is 1 over 2. That's what you do, an average. Most people do averages. Number 3. There's no reason why you can't have an optical curve effect. He didn't mention the word optical, but he said if I had a light wave, that I could modulate my index, however my lamp only puts out 1 volt per second. He knew Maxwell's equations. He knew it, and he mentions this. Not until 1969, with Bell telephone, with Gay and Hansen, showed Gay, demonstrated the optical curve. He must have read this paper. And they told people like this at that time. I knew, I didn't know this happened. The years ago, the guy did this great experiment. He introduced the optical curve. That means they used the laser field with picoseconds pulses to reduce an index. To introduce. So where am I? Yeah. Okay, thank you. Yeah, see that close. Okay. here's where the assumption comes in, not an assumption. The laser field is E, you got a pulse width, that's the envelope, and then you got the phase. There's the pulse, there's the phase. And then there's the big hands there. This is where the end comes in. That's the end. That's the end. You see the end. You'll see this later. So we show that the phase gives rise to higher harmonic generation and cell-phase modulation, while the envelope only gives rise to the cell-phase modulation. We'll show this. Now, the N2 that you have has a response time. There was not taken care of. Here it is a response time. And there's various mechanisms. So I'm going to go over this pretty quick. The electronic cloud, that means when you electric field on the cloud, it distorts. That occurs on a time scale, maybe 150 femtoseconds. That's the time for a Bohr orbit. I took 1/3. So 1/3 of the Bohr orbit is 50 attoseconds. So from 50 attoseconds in a mechanical period to about a femtosecond, you have the distortion of the electronic clouds around the atoms. That's called electronic cloud distortion. That's very fast. Then you have electrical redistribution, which means dipole-dipole interactions associated with changes. That's also very fast, but it's not as fast as the electron. It's like a tenth of the people say. Then you have the slow stuff, which is like rotation of the molecules, say CS2, nitrogen rotates, vibrates, and these are around 2 picoseconds. And you have plasma formation. If you ionize it with gas or ionize it with also about 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ This is another slide showing the same thing. Editors of sun, electronic cloud, distribution, ionization, plasma formation, rotation, vibrations. And each one has a size and a response. You'll see this in a minute, how this mechanisms affect HHG. Now, we say the current material is only a laser pulse, so you have a response time to the laser, to the laser coming in, you have a response time, and essentially you have to get this function. Oh. The response function to the N2 is N2e squared, where you have either a Gaussian, or you have a weighted factor, you put a damped response time ratio into this thing, you define index refraction, not instantaneous responding. You have some averages in body, some averaging of NFT. But this is the key. This is the key. Very simple. I have to admit, it's very simple. Simple was always, I was always told, simple is better. God gives you simple things to work. He gives physicists the tools to work. So here's the electrical dimension of that. Envelope, phase, index of refraction, index of refraction. You stick the index of refraction in there, and you have, if I transform this, you get equilibrium. Straightforward. I had a hard time getting my papers published recently. There's a sequence of pulse of papers, 2020, 2023. There's a couple more, but it's just the same thing. Trying to understand what determines HHG. I'm trying to make the simple stuff. And we go back to 1970, the glory year. That's when I was at General Telephone. 1970. Me and Shapiro, this guy Shapiro, General Telephone decided to go into the laser business in 1968. They decided, our telephone business. They said, we have to get this, we have to get this. So they formed a team. Out of the 200 guys they had, they picked 7 or 8 guys to form this laser group. And I had a great boss. He's the only old guy amongst all these young kids, really young guys. And he was the only older guy there. He said, go out and find a laser. So he said, go out and find a laser. And come back in a week. Let's see what you can work on. The boss is upstairs, so she's near the third floor General Telephone, 3 stories. The Bayside Queens, they were called the wizards. They would determine what we do. We didn't determine, they determined. You look on the screen, you see a yellow dot. There's a laser going into a piece of glass. There's a colored Corning filter that eliminates the laser. Only the blue side, only the red side. And you see on the screen a yellow dot. This is what people say to us. Unbelievable, piece of glass. Now, why do we choose a piece of glass? I have no idea. We went to the machine shop, which on the telephone. Machine shop, that's what we call it, an optic shop. I told him, what do you give me? An optical material. It's a piece of glass. I said, give me a piece of glass. Come back tomorrow. I got this piece of glass, polished all sides. Maybe you get that done today. Instantaneous. Anyway, bring a piece of glass, send the thoughts in. This is what we saw. And this is now using a femtosecond pulse. There's a liquid cell, there's a target. You put in a red light, look at the red light. You see it. All of a sudden, at this point, the pulse is going through, you start to see the light. You see it. Unbelievable. Even today, you see it. Nice beams going on. In those days, as Peter would know, we used to have a single shot, right, Peter? Single shot. And that patience, Peter was one of my best PhD students. And patience was the key. You had to say single shot and then take a measurement, take a picture. Nowadays, they spoil these students. Nowadays, it's on all the time. Right? Everybody sees these CW lasers, double-signal lasers. They're spoiled. And then they say it's too hard. Are you guys crazy? In those days, we did sophisticated experiments. This is the picture showing you what you get on the output. Not only in this white light, depending on the cell, but then obviously the generation, you have to have a thin flow cell now. It's for the liquids they do. You see that higher generation. You have to have a lot of factors. You have a lot of stainless steel. Stainless steel. Expensive stuff. You gotta be rich. And this is a simple model, so you leave the store and say, oh, that's all it is. That's right, that's all it is. This is a simple model that was developed in 1970. They published this paper each year. This is our phase. Animated to you, and omega is the end. See, that's it. It's your laser pulse. It's your laser pulse. And you write the phases there, because there's the one. There's the index of refraction. There's a curve factor. You stick the curve factor to the phase. If you're ready to do that, you get this 2 minutes of the derivative of the phase is a new frequency. New frequency. Take a derivative of this, you get omega. This is time derivative of this. So it's a time derivative of the intensity. E squared is the intensity of the electric field. So take the derivative of this, you get a sigmoidal shape, and it generates a negative sign. The frequency, which depends on the nonlinear index, the intensity, Z over the pulse width. So the broader, the shorter the pulse, the more broad you get. So it depends on N2IZ. The simple model. And the Fourier transform of S of t is what you get from when you get your field in, you get the frequency. It's the same slide. Again, I put it earlier, is to show you what happens with using that theory. So when we go into now, we'll be going into this part. Okay, so to generate these high harmonics, whatever you can say, high harmonics, from the curve factor. This is the key. The people who are the pioneers in this HHG were stuck until maybe 3 years ago, stuck on this tunneling, acceleration, and return. That's the mechanism of generating high harmonics in these noble gases. Tunneling with the atom, acceleration of the electron, and then return on return. It makes this And I'm saying, that's okay. It doesn't work for the solids. This guy Rice, or Reese, safe to say, he's not happy with that theory. So at the same time, we were publishing this paper, he comes out with the fact that that's this motto cannot be used for solids and liquids. This three-step model. You'll see that in a minute. So here's the theory of what we call electronic cell phase modulation. The Unix reflection follows the instantaneous phase. That I showed is rise to HH2. I showed theoretically, not experimentally. And you'll see in a minute. So here's the end. We got this already. We know that. Pulse width, cosine squared. Phase is that. It's in there. It's the end of the order. And you stick this N of t into the equation for a wave. Now, again, a wave, I'll let you feel of a wave already, Pulse width drives the cosine, there's the N of t, there's the N of t, and you have the N2e squared in there. So it's the cosine of the cosine squared. Cosine of the cosine squared. Didn't realize that at the time, but like I said, 1972, they said that. Now they're going to more. E of t is the last whoa. E of t. This E of t is the cosine of the cosine squared. That is key. Gives rise to Bessel functions. So mathematically, if you assume the wave going into a nonlinear media is the cosine of the cosine, and that generates these Bessel functions. And you do a calculation, you come up with that swing linear. You get a curve. This is that characteristic curve, which is these harmonics now. So that's the laser frequency, and these are all harmonics. And you got increasing time of plateau, and then it cut off. This is 41 harmonics. So, and it turns out that a method of stationary phase of this leverage wave comes out with an I0 over lambda squared. That's what it says. This theory of RE. I'm talking to Krauss post-op, and he brought up the point. The theory doesn't agree with quantum mechanical theory, which goes as lambda squared. That theory is I0 lambda squared. That means longer pulses generate better harmonic generation. So it doesn't make sense. But the theory shows that, and it's got a cool lambda. The pump wave is the key. I'll explain it in a minute. Maybe if he forgot something, their coolants, whoever they are, forgot ELM, forgot ELM. They forgot ELM. It's 3 times just like make that number forgot ELM. Because they calculate the dipole, they calculate the dipole. They calculate the dipole, which is the dipole squared omega. They calculate that. And they plotted the dipole strength as a function of Planck wave. Repeat, they plotted the dipole moment calculated from quantum mechanics versus the frequency. And they forgot it's the dipole strength. The dipole is not the thing that's radiating. I mean, it's not the thing you see. But you see outside your sample, you see radiation, you see intensity, you see dipole radiation. That dipole radiation has an omega to the fourth power. There's an omega to the fourth power on the dipole. The dipole is the strength, and you get multiplied by omega's fourth power. When you put that all together, you get that dependence. I think I reconcile this big problem. They say my theory is not right because it doesn't follow. But like I said, everybody here it was a channel. Canada, I was in Canada. Canada is still an American. I used to be at Allison Wonderland. He was in Kansas City. Kansas was in Kansas, in Florida. Now he's in Canada. He's on the air somewhere, I think. He's giving him another talk later. And also from Lewis, you have to realize, I need more supporters. They said maybe it has some value, this theory of electromagnetic. Again, they calculated d squared versus omega. Write that down, please. You calculate, I don't know if you, but they calculate d squared versus omega. And they get 1I times lambda squared. But that's what they plotted. They plotted the strength of the dipole emission, not the strength, the dipole moment, not the strength of the dipole radiation, which is the Poynting vector. The Poynting vector squared is proportional to the dipole moment times omega -4. It's like light scattering, omega -4. I'll explain that maybe later. I'm not sure. I remembered it now. I have to remember something I say it. So let's remember that. So that it says that quantum mechanical, which is IP plus 3UP, the ionization plus the polarity, is the cutoff frequency of I0. Obviously in conflict with this. Obviously. But these two kinds of things, with the E and M curve. However, I say, I can reconcile that. You'll see later part of the talk, which I just gave you a synopsis of, that you don't calculate D. You calculate D, you have to multiply that. I'm setting that up for multiplication. This is the curve. Now, from the calculated spectrum we measured by the Kerr effect, we get a dependence. And it's like this. This is the cutoff region. Depending on population. Cutoff frequency. That is the frequency. That is this. Cutoff is at the end. That's the end. It's also important that this intensity dependence also is cut off to zero. The end of is the plateau, is the end. Cutoff region. It's this determination. The cutoff region is the key to these people. And we plotted this. This is what we did. Our theory is. Our theory is type of dependence. Pump rate 500 is better than 2,000. Remember, cutoff wavelengths are much larger than physical. This is from our theory calculated what it is. Now, this is the standard that won the Nobel Prize. Not based on this model, based on people working in the out-of-second business who did out-of-second research. And first, and this is the theory based on electric dipole transition, or higher generation, based on time-dependent Schrödinger's equation by Lewis, Corcoran, and a bunch of other people. So this is the theory. There's the atom, and you put your field. Then bends, the electron comes out, it's tunneling, it accelerates in the field, and then it returns. On the return, it emits all these frequencies. To the best of my knowledge, I don't see where this model gives you this higher model generation picture. How does this select the different wavelengths to give this curve? This is the curve, this experiment we see. A decrease in the harmonic generation, a plateau, and then the cutoff region. So the different colors, decrease, plateau. This is all. All these modes are locked. Remember, these modes are locked. Why are they locked? You know why they're locked? They're locked because it's generated by the calcium. This locking these phases. That's where the mode locking comes from. You ever mention this theory? They lock them. How do you start getting out-of-second pulses? You gotta have mode locking. So the current mode locking is active in this theory. Well, it's different again from the theory that was generated. This is the theory, this is the correct theory. I'm pounding this into your brain. So there's a wave. Everybody hopefully accepts the ansatz. That light is a wave. Envelope, phase, and mixed refraction. In mixed refraction, Kerr effect, stick this in, you do a Fourier transform, you get S omega, and you get this. This is the first paper I published. And you get the three regions. 1, 2, 3. This is the decreasing part, steady decline, 3 regime, plateau. From this theory, whoops. From this theory, that you have here, 1, 2, 3. And one tissue point around each harmonic, you get a continuum, the self-phase modulation within each of these harmonics. It's broadening. That's another feature of this theory. Giving the cool end of theory does not do that. Does not explain that. This theory is much better. I have a bias. Okay, the key points of the high harmonic, I guess I'll just keep on driving this. This is essentially a wave, Kerr effect, but now I say E squared is equal to the cosine squared. So the cosine of the cosine squared, this is cosine squared there, and this gives rise to Bessel function. So now I'm going to show you, without doing a Fourier transform, not necessarily do a Fourier transform to go to vector space. Just expand E of t. You just expand E of t. This showing you, this slide shows the response time of the curve medium, like this. Response time. How fast does the medium respond? So it turns out that less than a femto, 1/10 of a femtosecond, you get this. You start making longer the response time, 1 femtosecond. The number of harmonics almost disappear. So the medium is very important. The curve medium is extremely important to generate high harmonics. And this has to be the self-phase modulation around each of the. This gives you a picture of the number of harmonics. This is the response time. So it doesn't work for response time, not the pulse width of the laser. By essentially the response time. So this is for argon, this is zinc oxide, this is something else. So it shows that the number of harmonics depends on the critically on the response time of the curve medium being on the order of less than a femtosecond. What is that point to? Less than a femtosecond? Some kind of electronic mechanism for the nonlinear coefficient. Now look at this pulse. Variation of this. So there's the envelope. Inside the envelope of 100 femtoseconds, you have a number of cycles. They're about 3.3 femtoseconds per second. Remember that the higher harmonics generate for the response of less than a femtosecond. So just the beginning of each of these pulses generate higher harmonics, beginning of these pulses. So the more of these frequencies in the pulse, the more cycles you have, the more harmonic generation you should get. Not the opposite way. If you're saying that the cycles are wavelength, they say 1.5 microns is better than 1 micron, it's better than 500. That is not correct. Right? Based on a simple cartoon, it says that the more cycles you have, which are in the pulse, the more you get. So therefore, a higher frequency, just like the electromagnetic model shows. The electromagnetic model shows that the more cycles you have, the more harmonic it goes inversely to the wavelength. So the shorter wavelength is the more broad. Now this thing I haven't had time to just over, but this is the theory that's in this paper, where it turned out 1972, we did this, 1972. We generated entities and put the N2 into the electric field, expand it. If you do this function, cosine of cosine gives rise to Bessel functions. You can calculate the number of Bessel functions, and it turns out that gives you very fifth set. But of course, this is my thesis paper. This is my PhD thesis. Unbelievable. I go back to this and say, how did you do this? I don't know. And also, in 1987, we did a key experiment at the City College. We sent in the PHOTONICS pulses. They were 106 microns and generated the first generation. We sent this entire light. And one. So in 1969, the first experiment showing that you got this theory supported. But again, we did not go to the fourth harmonic or the sixth harmonic because the detectors are different. That's the basis of the theory that I showed. This is more expanded. You'll get this slide more expanded. Expanded. Oops. More expanding this curve. You get all the different terms. This gives you K, blue expansion, K1, you go over to what you want to get. It's the fifth harmonic, the third harmonic, seventh harmonic, fifth harmonic. This is all classical, but I'm doing a Fourier transform, so we go directly to BFT to show that you get these. And here, believe it or not, it's a Bessel function. So my students show up, essentially plotted out the peaks of all the peaks of the Bessel functions. Just plotted the peaks. These are all the Bessel variables, this amp side, right? But he plotted the peaks of all these, he plotted it again. He sees this. What would you see when you do a simple experiment? You see the decay, the plateau, and the cutoff. Unbelievable. But you get all these information from the Bessel function experiment. And then let me just briefly talk about Addison. So you have these three regions. 1, 2, 3. And that's an evil matrix of making it. And you got the delta functions as well. And you know about low-lot places that Peter does. You see that you have lock modes, and they're all the same. And you got phases, and you lock the phases. So you got all these, you usually use something in the cavity to low lock the phases. The big problem was on sapphire, there's nothing in the cavity except the crystal. And in the crystal, you have N2 low locks. The low lock oscillates, low lock is sapphire. That's the key. And if you use Heisenberg's transfer unlimited, 24, to 0. This is a train each mode. It's 2 minutes 0. You calculate easily 4 hours seconds. Complement 31 modes. You got to couple 31 modes to generate on the flight to 31 modes to generate 4 modes. So then you say, oh, that's true. Instead of making 31 modes, let's make 300 modes. 300 modes with a modern couple 300 modes. You get 400 out of a femtosecond. 400 femtoseconds. You can generate femtosecond with this model. You're going to get more modes. In 1300 modes, 3100 modes, flat region, you can get yourself 40 femtoseconds. It's extending this model. Which one's so first? So, as a quick problem, we can set up a problem. So, as I said, cutoff frequency is the end. When you curve out of one of them, there's the quantum mechanical time resolve. Seems to be a big contribution. But it's not true. It's not. It just means that people, in some ways, didn't do it totally correct. The theory says, in 1972, we used quantum mechanical dipole evolution kind of demonstration. If you do that, you get higher than mainstream. Their theory is this. Along the way, well, we already know from the simple model that's not true. It appears it's the radiation you want. The radiation not the strength of the dipole, not the strength of the dipole. The strength of the dipole is here. But the dipole emission, if you know me, and I teach you that. I used to teach you, I teach optics now. But you know it's d squared times this is the dipole emission. At the energy, you are measuring the energy. You are not measuring by itself the strength. The strength of the dipole does vary over this, but you're going to multiply it. So you're looking at the dipole emitting, you're measuring intensity. And if you do that, you get an area of the square. The concentration seems to be over, I think. We haven't published this yet. It's in the print, it's being reviewed. Hopefully it's rules will change. Somebody that I know, not some under cabal that is here with this step. But they don't get Nobel Prize for that stuff. There's nothing to talk about. Somebody would know. You'll got your place. So. Okay. So essentially, I'm ending now. The idea is these papers, if you want to take it down, these are the key papers that talk about these high harmonic generation, speed from the electronic self-phase modulation. It's all theory, high harmonic generation. The current median response time is the key. Hopefully, it'll be a level to what is the key point is to make three regimes can be found by electric self-phase modulation. You can generate out-of-second pulses on mobile basis from the harmonics. You get even and odd, which the other theory is not giving even and odd. Which you play around with the wave functions and so on. And it's possible to generate separate studies that copy large modes of the higher harmonic. People from Colorado may be able to do that, and I think we'll just do this in the industry. It's good those to sit in there doing. We'll talk. This controversy, so I think I have what it does exist. And there's all these different characteristics I have, but I have 1 minute. I'm a chair. I say yes, yes. I say yes.
Yes.
Yes. So this ENM model, has a lot of things in it that can be included. The assumption, he is a wave. Assume instantaneous index of diffraction. You can explain the curve effect, measure from the empiricists of something else. And then you generally need the parameters. You don't have these parameters that you play around with the timers of N2 and 1 or 0. Something you have. And the spectral broadening around each peak. So you look around each of these peaks, along you have a broadening. And it's really the best of functions to use the EMT and mode locking. You can explain curve mode locking, it's curve mode locking. And you've got to say, where is the curve mode locking? Every one of these lasers have an aperture. I believe everybody in these high harmonic business with the flowing jets have an aperture. That's the aperture is the mode lock. Aperture of the mode locks. High harmonics. It was high harmonics. And let's say I find it's possible negative frequencies in the year that real resistance that can generate. What is the meaning of this? What is the meaning of negative frequencies? I think you don't have to talk to anybody. We get negative frequencies. That means it's in another world. It's in imaginary space. Most important, you can test this laws. What's the thickness dependence of your serum? Thickness, you can do experiment. Hopefully, my student will be alive this summer. He's supposed to have to do some of these experiments. We're going to do the ability to lose weight. If you had a major accident in college, I had a dust storm period, I wiped out my whole body. The insurance company came through with all the equipment, I got all the equipment now. So I got a new race there. Before the corona happened, we got new laser service. Oh, this is a cartoon that supports my eye over at this way. Here's your pulse, 150 seconds. There's 1,000, there's 500. Notice the number of cycles. Oh, 60 peaks, 500. If you say the beginning of each of these things generate harmonics, then for 150, there are 30, and then 60, there's 2. How do you explain it 4 times? Well, I explain it because it's close on the square. So it's square number 2 before. That may explain it, but definitely, without question, 500 generates more peaks and broader waves. No, idea?
In a real pulse, you're likely to have the least residual chirp. Does that make any difference?
Oh, sure. This is not chirp. I didn't do the chirp pulses. That definitely affects things.
Is it a feature or a bug?
It's a feature of love.
Right? Does it help?
No, I don't think it helps. I think you want to transform it into things. Because remember, you want the continuum to be symmetrical. So you have a symmetrical pulse. You don't want to have red and blue in the middle. Moving stuff over here. You want to lock the modes. That would make the modes not lock very well. So I think it's critical to have the pulses coming in and transforming it. I think it's good paper. Definitely, I must do the check on input and see what happens. Yeah, it's very good idea.
This cell phase modulation can also be used to produce a contrast in the image that if we focus.
Yes.
So in that sense, can you comment on how much energy, pulse energy, nanojoule or microjoule?
Anyway, you need at least a microjoule.
Microjoule energy.
To come in to get cell phase.
But this under microscopy is very hard to focus.
Well, that depends on the nonlinearity of the material.
Yeah.
I mean, it depends on what's in the material or not.
I guess
You're going to hear about these response time. Most materials are based on picoseconds or material absorbed during the imaging, so it's not very much continuous. But all materials have broad. All materials, any pulse coming in at a microjoule, even less than microjoule, generate a broad. So therefore, that can help you or kill you with your image. But if you have a picosecond pulse, you don't have any broad. So if you're coming, most of the people, or actually postdoc, stimulated mom. She went from Columbia to California, and she's one of the supporters of this conference. And she does a lot of stimulated mom, and she was going to have the option of buying femtosecond laser or picosecond laser. I told her picosecond. She does stimulated mom. The stimulated mom only works picosecond. If you have less than a picosecond, you're not even for it. So most people do imaging. Uses picosecond pulses. When you go with any source or simulated on, use picosecond. That's the right way to go. If you go lower, sure, it's like have the best laser in the world, so you can buy a femtosecond laser. That gives you blood. Glory. But you have to use filters. You have to use filters to separate the waves. So, yes,
one thing was, so first of all, the N, the definition of N, that can come out of quantum mechanics as well.
No,
it's a classical statement, but you can derive that from quantum mechanics.
Of course, you can derive anything from quantum.
Yeah. So in fact, one version, it's just to go back to the Desi theory, so you can get that expression.
Let's go say
So
But
So it's quantum mechanical, the treatment as well.
Well,
Yeah.
I could convince the editor, this girl, Ann Paycock.
Well, that's, I just want to make that comment. But
I was also that's
the,
true.
the other thing was, so to put in.
I didn't say, I didn't really be clear. I didn't say that the anti you went to the, is it is the standard, it is the fact, get that from quantum mechanics, it's there.
Right.
And I'm just using that and,
Right.
and even if it's,
That's perfectly legitimate. So to put in the response time, then you have to go back to your the F function on your
Yes.
slides. Okay. So did you ever do that? I mean, so you're making good arguments for the
I did
response
that.
time. Oh, you did that in your calculation.
yes, because they're called slides.
Okay.
No, I did that, it was a plot, I bought a number of harmonics generated response time.
And that was from putting in something.
Put the response time of up to a femtosecond gives you the same. You get to about a femtosecond, stuff that you could cut off gets short. That's in these papers.